Alright, so today we're going to talk about a problem from the Princeton University physics competition in 2015. I was a participant that year. I didn't do that well. Um, it was enjoyable nonetheless, so this is one of the problems I like, problem one. And basically, so the setup of the problem is you have a small mass M, on a spring, and there's like this loop-de-loop sort of thing. And so the first part of the question, and this is like has a radius r, and the original question, the 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 mass here has a small radius little r, but I'm just gonna ignore that and treat it like a point mass, and the physics is pretty much the same, the techniques at least. So I'm gonna say r is like little r is much less than big R. So the first part says, okay, what's the minimum distance you have to like stretch this so that it can complete a full circuit through the loop without like losing contact with it. And so the first thing we can do is we can figure out, okay, what is the minimum velocity I need here so that I don't fall, right? Because that's the part we have to worry about. When we're at the top of the loop, we don't want to fall, right? So when we're at the top of the loop, we want the normal force, which points like this, we want that to be minimized. So we want it to be 0. And so in that case, the force here going this way, which is a centripetal force, mv squared over r, we just want that to be equal to gravity and plus the normal force, right? But the normal force is 0. And so then we can solve, and we get v squared equals gr. So that's nice, okay. So then we know how fast we need to go. So now we can make like a conservation of energy argument, because when we compress it here, all the energy is going to be potential energy because the spring is compressed. The ball's not moving yet. It's not. If we set this to be like y equals 0, there's no like gravitational potential energy. It's just a spring potential energy. So E initial, or energy initial, is just the potential energy in the spring, which is 1/2 kx squared. And ultimately, we want to solve for x. And so we know that energy is going to be conserved. And so we can actually think about this point here, since we know the velocity at that point. So we can compare the energy we initially have to the energy at top of loop, which should be the kinetic energy plus the potential energy. Now, one other important thing I should mention is this problem also tells you that the little mass has a moment of inertia I equals 2/5 m little r squared. And so with that in mind, we can break up this kinetic energy into the translational kinetic energy, which is 1/2 mv squared, and the rotational kinetic energy, which is 1/2 I omega squared. So let's see, we can write this here. E at the top of loop equals 1/2 mv squared. Well, v squared is gr, so this is 1/2 mgr plus, what is the potential energy? Well, the potential energy due to gravity is mass times gravity times the height. Well, what's the height? The height is twice the radius, so 2 mgr. And then plus the rotational kinetic energy, which is 1/2 times I, which is 2/5 m little r squared. times omega, but we know omega is v over little r, so we can substitute v squared over little r squared. So then we have that this is equal to 1/2 mgr plus 2 mgr plus, let's see, that's 1/5 mv squared, but v squared again is gr. And then if we add this all together, let's see, 2 plus 1/2 is 5/2 plus 1/5 is 27 over 10 mgr. So great. So now we're ready to solve. We have that 1/2 kx squared, the energy in the beginning, equals the energy at some other point, because energy is conserved. And if we solve for x squared, we get x squared equals 27 over 5 mgr over k. So x minimum is the square root of 27 mgr over 5k. And that's our answer for that part of the question. So the next part of the question asks, okay, well if you do that, how far does it get up the ramp, right? So if you compress it, how far up, if this is like the height h along the ramp, like what is h basically? And so we can figure that out using conservation of energy too. Let me get another piece of paper. And so we know we can again do conservation of energy, right? Because when it gets to its highest point, we know like it has to stop moving translationally and rotationally, and so there's the only thing that's it's going to have left is gravitational potential energy, right? It shouldn't be moving at all anymore, so kinetic energy should be 0. So the energy, the E at h, should just be the gravitational potential energy, which is mgh. But at the same time, because of conservation of energy, that should also be the energy we started with, which is 1/2 kx squared. And so one thing we could do is we just solve for x, so we could plug x back in. But I think what's easier is, okay, well we know that energy is conserved, so we also know that it's equal to the energy at this point, which was 27 over 10 mgr. And now you can see it's a lot easier to solve for h, because then you get mgh equals 27 over 10 mgr, so then h equals 27 tenths r. And yeah, that's it. So I guess one thing you should notice is that this r isn't like technically like the distance from the center is like big R minus little r, and then like you have to worry about all this stuff, but I'm just making this assumption that r is much less than r, so I don't have to deal, so that my answers can still look really nice, but the constants and everything will still be exactly the same. Yeah, when I took this exam and I looked at this problem at first, I thought like, because it was like a computer generated image, so this looks like a perfect circle, so I thought this was like another big mass, and like this would somehow like push it up the ramp or something weird. And then once I figured out that it was a ramp, I'm like, okay, well what about friction? Like I was really confused, but working on it again, I'm glad to see there's like a nice solution that uses some basic high school physics, and I think that's part of what makes this a cool problem. So yeah, hope you enjoyed.